Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. My name is Jim Chastain. The primary purpose of this series is to cover a bit more depth on specific aspects of the use of the tools, and some of the features may not be covered as often as needed in day-to-day use, so we title it a refresher, not necessarily a tutorial or training. But today we're going to discuss arc flash options. This is one of those topics that you can be exposed to multiple times, but until you actually run into the situation that requires that specific option, the stuff may not really sink in. I frankly speak from firsthand experience. So let's start with two poll questions. The first is going to be trying to determine who does data collection versus who does the analysis. So in your experience, how often does the person that collects the data also become the person that does the analysis? Appreciate some feedback. Nothing is formal by any means, but we do appreciate a little bit of a understanding who's in the audience and how their interests may pertain to the subject that we're talking about. So let's give this about 5 more seconds. Here's how things look on that particular question, which is interesting. And then secondly, from your experience, how often does it require multiple visits to the equipment or the site of the study to actually complete the data collection? And obviously the reason for this is actually what drives up the extra cost of doing a study, and the intent is try to help people understand what they're looking for ahead of time, and thereby being able to be a little bit more comprehensive on data collection and observing the system parameters and variables, some of which are affected by these options that we're going to be talking about. Appreciate the feedback. Here's how the audience looked on this one. Again, I appreciate everyone for participating. All right, so let's jump into the topic. Today's agenda is primarily on the arc flash options, and the point is that the better these are utilized, the better, and I guess that term is used advisedly, but the more, I don't even want to say accurate, the more comprehensive the study will reflect the actual conditions of the system. And so some of this is incorporated, frankly, some of the data that's required to utilize these options is incorporated in the tribal knowledge of the plant's maintenance team, and this does have an effect on the outcome of the arc flash risk assessment. And so if it's not properly captured during the data collection process and modeling, it may get lost in the process. And part of the reason that I suggest that the data collection and modeling process include as many as possible the team members that are involved in the day-to-day operations of the plant and the maintenance. Now, most often during the modeling phase, which is the time that the one-line drawing is constructed and the data for each of these elements is put into the system, the decision is made to incorporate these arc flash options. So there can be significant learning training about arc flash and what I refer to as the arc flash phenomena that will benefit the team members, specifically the qualified workers whose very safety relies on the correctness of the results of the study. So there's a self-feeding improvement cycle there, the more that the maintenance people are involved, not only in data collection, but in modeling the system. So I consider these to be very sobering statistics, and that is in NFPA 70E, the informative Annex K, and frankly this is an answer to a question that came, I think, from Leo a few weeks back, that what are the different categories of electrical arc flash, and at what level does it cross that boundary where you really have an explosion. So according to NFPA 70E, the 3 levels of hazard include electrical shock, arc flash, and arc blast, and this constitutes the majority of the incidents of human injury and fatalities And surprisingly, electric shock is the fourth leading cause of industrial fatalities. Blew me away. So just to take a real quick look at this, the arc flash will produce a region of plasma where the high heat levels are generated, and that's the air where the electricity is actually ionized the air between the conductors. And this in turn, the plasma ball in turn produces the larger fireball. With the same amount of energy, and the energy density is released in a shorter amount of time, it stands to reason the physical dimensions of the fireball and the plasma ball will be larger. And so the same energy released for a longer period of time may produce a significant fire hazard, but maybe with a smaller concussive force. Again, that's not quantitative at all, but we will get into exactly that comparison or discussion when we get to the low voltage section of the option. So I'm sure that didn't clear anything up, but hopefully it give you something to think about. Now, according to IEEE 1584, it's actually only one of several models that were generated to represent an arc flash, and it's become 1584 has become the de facto standard recommended for most systems in the application of IEEE 1584, the model developed in 2002. Now, it was developed by running a bunch of testing on actual arcing events, and then the model itself was developed by coming up with a series of equations that best fit the empirical data. So these applicable conditions for the use of 1584 and the calculation method represent the area where it's most accurate. Now, you'll notice that some of these ranges exclude the use of the model in many situations commonly encountered, particularly by utility workers. And so if you join us, I think during the next week or so, certainly within the next 3 sessions of our Tuesday refresher, we will specifically be going through the applications for EasyPower in the utility environment. Today we want to tackle the variables that are within this constraint and the applications that are covered by the model in the majority of cases. So the basis for the discussion, and those of you that haven't seen the 4 equations that I'm referring to, they are available both in the IEEE paper and in NFPA 70E. They're a set of 4 linear equations with logarithmic terms, and the variables are all related to the data that was collected during the IEEE test phase. Now, these are the variables that give rise to some of the arc flash hazard options that we find in EasyPower. So now I'm going to jump into EasyPower and see if we can't give some specifics in exactly that. All right, I'm starting from the start page. I've already got a one-line diagram drawn up here, and as many of you may have seen, once I've got the data collection completed, the model drawn, and all the data entered for the elements, I like to go in and execute a short circuit fault looking at the half-cycle current for a balanced 3-phase fault. If the currents look reasonable, we'll calculate the incident energy, and then the next step to really kind of verify that we're either on track or not, I want to use the arrange for arc flash icon in the center of the screen at the top. Now, one of the first things that jumps out at me, if I were doing this study, or if I had the plant, if I owned the plant that somebody was doing this study for me, is that, okay, well, what's going on here? I see a bus that has no valid trip device. What am I supposed to think about that? Well, that brings me to a discussion of controls, if you will, that are actually built into the database editor. So let me jump back into the database editor on this file and talk a little bit about specifically how to deal with this bus up here, which in reality, no one in my employ will work on this bus. It's a connection point between the utility and my primary of the transformer. But because it's part of the one line, it can confuse things if I include it in my report. So again, I'm in the database editor. I'm going to open up this bus. And the reason for kind of going into this is that every element, every bus in the system has all these same tabs. And we talk in terms of the number of tabs that are located in the center of the screen that need to be populated. Well, one of these tabs is the arc flash hazard tab. And when we start talking about options, these are the options we're referring to. For each element, and most of the time we're going to spend talking about global options, but each bus has the ability to override on a local basis the application of those global options. So for starters, and they reside in how we consider the main bus, the main breaker on this bus, and secondarily whether or not we even want to include it in our study. So in this case, to solve my problem of confusing my client because the bus that we're referring to really doesn't have any bearing on the discussion, I want to exclude this bus, and it just takes it out of the discussion as far as calculations. Now, as long as I'm here, let me point out a couple other things that are very useful, one of which is, now you notice that as soon as I excluded the calculations, this area became grayed out. On a particular bus, these elements are used for setting time dependent protective devices, and so that's something you may want to come back and have discussions on later on. There's also the ability to set the number of labels that we want printed on this particular bus. If we want to have 5 labels and we're going to put in some comments that would reside in this particular area and would be carried forward as we work with this bus. Another thing I want to point out, and this is a feature relatively new within the last 6 months on the EasyPower tools, is this frame over here, which is referred to as the media gallery. It's been added, and a normal operation for data collection is to take a host of digital images as we do the study. Now that we have the media gallery available in the database edit, we can actually add, let me see if I can find my images here. I've got a series of pictures that I've taken, and now I can incorporate any particular image that I've taken of this location, and it will be included in the file. And especially if I've done a good job of in the picture making it legible in terms of the details of this particular device. Now again, this is a transformer label that I'm attaching, so it doesn't really pertain to this bus, but nevertheless, if I take a good picture and I can read the data, sometimes that actually can save me a trip back to the site to make sure that I have accurate data. So a couple features that go a little bit more than just the options, but again, it will improve the process of making your study more accurate. All right, so I'm going to go back to my short circuit focus, fault the buses, look at the arc flash matrix, and again, now we no longer have that bus at the very top included in the analysis. Okay, there are 2 specific scenarios that IEEE requests, and that's another thing about some of these observations that are included both in NFPA 70E and the IEEE 1584 paper, and that is these conditions or these ability to tune the variables are not given to us in a nice short form list. They're kind of spread through the verbiage regarding the application of the model. Not to criticize it, but that's just the way it's done. One of the conditions that they describe that must be considered as an alternative configuration is to consider the short circuit currents and incident energy with motor contribution and without. In the database edit, EasyPower makes that relatively simple. If I pick an open area and right click to pick up the global options for the tool, it gives me the ability under the general options. I actually did that wrong. If I right click here, it gives me the ability to include the motor contribution or not. So right now my drawing as it stands is with motor contribution. So a good point to be made is store this scenario as with motors, save it, go back and uncheck that box, and now say this scenario without motors, and we've covered both of those recommendations from IEEE. All right, so that's with and without motors. The second scenario that IEEE recommends and pretty much requires as a consideration is to consider the 85% arcing current versus 100% arcing current and determine which is more significant. That's done automatically in EasyPower, and the results are shown here on the arc flash hazard report. The magenta type shows the 85% arcing current calculation. The dark type under this arc flash fault and trip time report, the dark type reports 100% current. And that is controlled in our short circuit options, which I'm about to display. So again, this is where the results are shown, where the control is made. Again, under short circuit options, short circuit focus, short circuit options, the arc flash hazard tab. This is where the majority of the options are set. And as you'll notice, some of this is duplicated on each bus data dialog box because we can override most of these settings. All right, in terms of the 100% versus 85%, that's a recommended comparison to be made, but these can be adjusted for whatever reason if our engineering staff wants to consider different points to do a comparison. And the reason is here, because the slope of the protective device, the curve on the protective device may vary, the lower current could actually produce a higher incident energy, and then again that's being reported on my arc flash hazard spreadsheet. Okay, next thing we're going to look at as far as options is whether or not to include the main breaker or exclude the main breaker on any given bus. Now again, what we're talking about, as you look at the one-line diagram, we're talking about the potential for having to work on this bus hot, the bus work itself, and whether or not this breaker, the main breaker upstream of that bus, will protect me if I'm inside of this panel. And during data collection, if I observe that there's no barrier between the upside cable connectors into this breaker and the bus itself where I may be working, it was observed during IEEE testing that the plasma ball or the arc itself could travel, so an arc that forms upstream could actually bridge the breaker if the plasma ball were large enough. And so if there's no barrier, an arc barrier between this connection point and the bus, then I cannot use the trip characteristics of this breaker. And that's what's being shown here. So if I apply this, what you see in the results in EasyPower is they give me a calculation that's higher, that actually be the higher arc flash boundary. If I were to select the including selection and apply it, it would give me a lower arc flash boundary calculation. Now the tool actually gives me the ability to include both, and when I do that, it'll give me two numbers referenced there, and when I go down to the bus, it'll give me two different representations on the spreadsheet indicating which protective device is in play. If I'm excluding BL4, then BL5 would be the next device upstream. And again, it has nothing to do with the confidence that this breaker will work or not work. It has everything to do with a barrier, a physical barrier that would prevent an arc from jumping from the input connectors to the downside or the bus side of this main breaker. Now, another option. By default, when we calculate incident energy, the tool is set up to use momentary current. We have the ability to produce or do calculations with interrupting current, and that will change based upon the level of current at 5 cycles, and we can do the same thing at 30 cycles. Again, it will change or not change based upon, frankly, based upon motor contribution. If we have, and did it set where I left it here? We come back here and look at it. Yeah, so on this particular bus, if we look at I have 0 motor contribution, so consequently these numbers won't change. If we go back and change that back to include motor contribution, go to short circuit focus, we will see those currents change based upon using 30 cycle or momentary. Right, and so we see the total incident energy change on the bus. Now, although it's not part of the IEEE model, EasyPower includes the ability to utilize a combination of these three values, and we refer to this as an integrated method. And what it amounts to is if the fault lasts longer than half a cycle or 5 cycle or 30 cycles, it uses for the period of time that current's available as far as the calculation for and summing for the incident energy. For instance, if we have a long fault and we're using the momentary current, we actually end up with a higher incident energy calculation, because if the fault lasts for more than half a cycle and we're using that half cycle current for the total time to extinguish the fault, then it's going to be conservative, but it's going to be a little bit incorrect. Whereas if we use integrated for a long fault energy calculation, during the first half cycle, the tool will use the momentary current. For the next 5 cycles, the tool will use the interrupting current. And for anything beyond that, it will utilize the 30 cycle current to sum up the energy on each particular bus. And I'm not sure that I have the differences in my, let's look at the energy and see if it changes. So if we look at momentary and apply, and let's go ahead and exclude it so we have a little bit higher results. And we compare that with integrated. We're looking at 1.2 calories versus 1.3 calories. So this actually is much more significant in higher current applications, but you can see that the net result. Sorry, so that's that particular option. Then we have the ability to display working distances in variable units. Everything right now is in inches. We also have the ability to calculate working distance, whether it's in an enclosed box or open air. In an enclosed box, we have re-radiation of reflected energy from the back and side walls, assuming that we're looking through the only opening in the box, and so consequently we will find higher incident energy as a result. And again, these are determinations, both whether or not we include the main breaker, reflecting whether there's a barrier there, or whether or not we're dealing with an enclosed box or an open air bus. It has to be captured during data collection. Another option that has bearing on this discussion is that of the default working distance. By default, these are set up in the standard library, so these default settings can change. But by default, we calculate working distance at 18, 24, and 36. If for some reason we want to include some other distance because we realize that there's a need to mitigate the energy and have the operator stand at a specific distance because of the ability to help our calculations, we can enter that number here as separate. So let's say we had some task on a bus that had a working distance of 28 inches, and we want to know how that applies to our system. So where I was entering this is in the voltage range 300 to 750. We want to calculate working distance of 28 inches. Let's go back to our short circuit, fault the buses, look at the arc flash hazard report, and where that will show up is in the arc flash hazard report at this positive or plus sign. We see by default the 18, 24, and 36, and now that I've added 28 inches as my optional working distance, and we can see how that gives us an arc flash boundary or an incident energy at that specific distance, and that will hold with any of the buses that we select at that point. Now, one thing that I want to point out while we're here is that I've picked up and I'm using an example that was made sometime prior to 2015, and I say that because I'm seeing the PPE displayed on each of the buses. Well, that's, again, not allowed in 2015 studies and beyond, and EasyPower allows me to control that with the option here under Advanced. So I'm the Arc Flash Hazard tab of the short circuit options. If I click on Advanced, on PPE level, I can show it on the label or not. And as I show it on the label, it's according to the lookup table on 130.7C. If I don't show the PPE, then I want to refer to the operator to the lookup table in NFPA 70E H3B, which is a description and allows us to dress, and as I apply this, you'll see it takes off that representation of the PPE. That allows us to dress to a level that's been determined as far as incident energy protection. But again, that's a useful part of the arc flash options. Now, I referred earlier to the business about, let me kind of close this out and find the place on my spreadsheet I want to play with. Now, one of the areas that's a little bit of a concern is that of low voltage. And so as we come back and look at this, I have a 208 panel, or in this case I'm calling it a 240 volt panel, and it actually falls just at the perimeter of the variables list that the IEEE model gave us, and that is 208 volts. So according to IEEE, we can still apply the model at 208 volts. The issue is, so let's go ahead and, so here's my 208 volt panel, a 240 volt panel. We fault the bus. We look at the half cycle current. 7,300 amps bolted fault current is significant. When we look at the arcing current that's the model predicts, we will see on panel 1, we still have over 3,000 amps of arcing current if that bus were to fault. So the question is, if we look at the incident energy, the question is, do we really have an arc flash boundary that's 57 inches? And this goes to the question about how long the calculations are being made. So let's go back and look at our options and see where we have this set up. First of all, we're including main, and in this case, we're excluding main, and in this case we have a fuse there. So let's just see if including main is going to help. And it does. The point is, what's the condition of this panel? Does that fuse really outside of the plasma reach if I have a fault just upstream of the fuse? Again, I can't make that call from here, and so I'm going to go with the assumption that I probably can't do that because the fuse is probably inside the panel and I'll be staring at it when I'm trying to work on the hot bus. Secondly, I'm going to use, we are listed here, integrated current. So I'm going to make this momentary because that'll make it a little higher. Let's see if that changes the world for me. Yep, that puts me back, by excluding primarily, that puts me back on the high energy level. Now this is one of the recommendations, and we actually have an apps note out on this for low voltage applications of the model. And the short version of the story is, during testing, IEEE had a difficult time sustaining an arc below 240 volts. They found that even when they initiated a three-phase arc at 240 volts, it would self-extinguish in less than 300 milliseconds. And so it really, to allow the tool to calculate to 1,000 seconds is unrealistic. If we look at this, where the panel is being protected by BL3, and again, BL3 is up on the primary side of this transformer, and if you've seen my example of the single fuse protective device, this is classic in that this is a real arc flash issue, but is it really an 8 calorie protected problem is the bottom line. All right, so let's go back to our options. What other choices do we have? According to the apps note, and I encourage you to download it from the website if you haven't already, and it's called Calculating Arc Flash Energies for Low Voltage Circuits. It recommends that below 250 volts, we can actually limit the calculation time to something much less than 2 seconds. And so if we consider a half a second to give us almost 100% guard band versus a natural the natural life of an arc at that energy level or that voltage, then there's some reason to believe that would make sense. Except in this case, it's still not giving me the amount of protection I want. And let me just say a couple words on time in general. There's another reference in IEEE about the time limit on maximum calculations. I like to start with the 1,000 cycles. That's the default setting. I see many times people will come in with 2 seconds on their general setup, and the significance there is that, and the basis for being able to use a 2-second limit on calculations is that if we are in an environment where we have an explosion or an arc flash event, then a person should be able to remove themselves from the danger area within 2 seconds. And so putting a limit of 2 seconds on the energy calculations means that we're going to produce or be wearing PPE that will protect us for the time that we're in the arc. I'm not sure how comfortable I am, and it really depends upon where I am in the system and the absolute short circuit current available There are certain places where I may not want to limit my arcing time calculation to 2 seconds. I'd want to know what it really is as far as the trip devices. And that brings us back to the instant energy for a panel. Same thing here is that, well, let's kind of go back and look at this. If I look at my my arcing current of 7,000 amps, we already discussed that the bolt default current is 7,000, the arcing current is 3,700. I've got two choices. I can take steps to make sure that, in fact, that would be my preferred procedure, rather than shortchange the calculations being made here, make some provision to move this protective device outside the panel so that when I go to my calculations and look at my short circuit options, I can actually include the protective device. By including the protective device and showing the energy, then I put myself in a safer condition than I am with that protective device inside the panel. So that ends up being the answer. Playing with the calculation time doesn't solve what appears to be the real issue here, and that is a poor location for the protective device. So if I can erect a barrier, or if I can move that protective device outside the panel, so and preferably far enough away from the operator so he can work on this panel without fear of an explosion at the fuse, then I think life is going to be much better. Okay, I think I've run out of time. For the most part, did we cover everything that we were looking at? Let's see here. I think so. We've put up on the website all the regional training for next year, and you're more than welcome to contact tech support at easypower.com. And by all means, if you have suggestions for future topics for the refreshers, we're open to that feedback.